Hello friend, welcome to my channel. In this video, I'll be talking about recurrence relation. So without any delay, let's get started. First, I'll define what is recurrence relation. An introduction of recurrence relation. This video I'll talk about the introduction of recurrence relation. So recurrence relation is an equation which defines a sequence recursively where the next term is a function of the previous terms. So recurrence relation is nothing but an equation which defines a sequence recursively. Where the next term is a function of the previous terms. Okay, let's give an example. I guess you know the Fibonacci series. Let's recall what was Fibonacci series. And the terms of the Fibonacci series was first starting with 1, then 1, then 1 plus 1, 2, then 2 plus 1, 3, then 3 plus 2, 5, 5 plus 3, 8, 8 plus 5, 13, and so on. So this was the Fibonacci series. So if I tell you, find out a general expression so that I can write down this Fibonacci series. And this general equation, general relation is nothing but that recurrence relation. That recurrence relation is given by Fn equals to Fn minus 1 plus Fn minus 2, where F1 equals to F2 equals to 1. This thing is called the initial value. Okay, and this is our recurrence relation. We see the third term is nothing but the addition of first two terms. The fourth term, that is F4, is nothing but addition of F3. So this is F1, F2, this is already given. F1, F2 is 1, this is F3, this is F4, this is F5, and so on. So you see F4 is nothing but F3 plus F2, because F4 is what? F4 is 3 is equals to F2 is 2 plus 1. So this equation is the recurrence relation of Fibonacci series. I guess the idea is pretty clear to you. What do I mean by recurrence relation? Now I'll talk about the types of recurrence relation. How many types of recurrence relation we may have? Okay. First is there is two types. Broadly, it is classified into two main types. First one is linear. Second one is non-linear. Linear recurrence relation and non-linear recurrence relation. Now, what is the form of a linear recurrence relation? The form of linear recurrence relation is like Fn is like C Fn minus 1 plus D. this is linear in Fn minus 1. So this is a linear recurrence relation. Whereas the example of nonlinear recurrence relation will be Fn equals to say 1 by 1 plus Fn minus 1 into Fn minus 2. This is one of the example of linear recurrence relation. Nonlinear recurrence relation, sorry. Now this linear recurrence relation can be mainly divided into two main categories, which is homogeneous. Another one is non-homogeneous. Okay, I'll see the example one by one later on. Okay, now this homogeneous linear recurrence relation can be categorized into mainly two categories, which is constant coefficient. So linear homogeneous constant coefficient recurrence relation, this is non-constant. Okay, so we have linear. Under linear we have mainly two category, which is homogeneous and non-homogeneous. Under homogeneous we have main two broad category, which is constant coefficient homogeneous linear recurrence relation and non-constant coefficient homogeneous recurrence relation. Similarly, for non-homogeneous also we may have two categories. First, constant coefficient and non-constant coefficient. Now let's see one by one the examples of these types of recurrence relation. Now first one I'll give, which is linear. Now the linear recurrence relation is, I already said Fn is equals to like some C times Fn minus 1 plus D, where C and D are constant. This is linear in Fn minus 1. Okay, someone can give like n Fn minus 1 plus D. This is also linear. Though n is multiplied with Fn minus 1, I want to mean that linear in Fn minus 1. We will not look for that n terms. Okay, this is linear in Fn minus 1. Fine. Now I will come to linear homogeneous. So linear homogeneous. Okay, the same thing, Fn, C Fn minus 1 plus, so D is 0. If we put D is 0, this is an example of linear homogeneous. Okay, similarly one can have n Fn minus 1, put D equals to 0. So this is also an example of linear homogeneous recurrence relation. Now come to linear homogeneous and constant coefficient. As I already written, Cn equals to Cn minus 1. This is homogeneous, but see, this is a constant coefficient. Whereas linear homogeneous non-constant. Example is Fn is equals to n f minus 1. This is C. C is constant here. Here C is a constant. But here n is not a constant. Okay, n is a variable here. So this is a non-constant coefficient homogeneous linear recurrence relation. Now come to the non-homogeneous. Linear but non-homogeneous. Okay, which is given as Fn is C Fn minus 1 plus D, where D is constant and D is non-zero. See, when D is strictly non-zero, this is an example of non-homogeneous linear recurrence relation. Okay, similarly, linear non-homogeneous constant coefficient. Yes, this is very simple, like fn c fn minus 1 plus d, that same thing, where c is a constant and d non-zero, also d is a constant. So this is an example of linear non-homogeneous constant coefficient recurrence relation. Now linear non-homogeneous but non-constant coefficient. This is nothing but n fn minus 1 plus d, when d is non-zero and d is constant. Okay, so this is the examples of linear and under linear homogeneous, non-homogeneous, constant coefficient and non-constant coefficient recurrence relation. Okay, now one can have a look about non-linear. I'll not talk about much about non-linear recurrence relation. The non-linear can be anything like which is not linear in fn minus 1. So one can written down as 1 by 1 plus a minus c fn minus 1. One can write down 1 by 1 plus c time fn minus 1 into fn minus 2. One can write down fn is equals to fn minus 1 into fn minus 2 plus, like, say, c. So this is all our nonlinear recurrence relation. Okay, now I will tell you. Now the question is, to find the solution of the recurrence relation, we want to determine fn in terms of n. Like, what do I mean by solution of a recurrence relation? So what do you mean by solution of a recurrence relation? So solution of a recurrence relation means we want to find out fn completely in terms of n. Okay, I repeat, we mean to say that the solution of a recurrence relation is nothing but we want to find fn completely in terms of n. Like, say, fn is equals to cn fn minus 1 plus d. So this is our recurrence relation. Now the solution of the recurrence relation means that we want to find out fn as a function of n completely in terms of n. That's very important. So this is an unknown function. So to calculate fn, we need fn minus 1, but we do not know fn minus 1. To calculate fn minus 1, we want to have fn minus 2 in our hand. So this is a recurrence. But here solution means we can completely determine fn. So fn should be a function of n completely. Okay. So to clear the thing, to make the thing clear, I'll consider one problem. Let's solve this problem. The problem is, check that n to the power n plus 1 is a solution of the recurrence relation an is 2n minus 1 minus 1. Okay, with a1 is equals to 3. Okay, now say we have a1 equals to 3. Now calculate a2 using this. So a2 is put 2 instead of n. So a2 will be 2 times a 2 minus 1 a1 minus 1. So we already know a1 is 3. So that is 2 into a1, that is 3 minus 1, this is 5. Sorry, 6 minus 1. Yeah, this is 5. Okay. Oh, I forgot. So a1 is 3. Now put n is equal to 1, this equation. So this is a1 is 2 to the power 1 plus 1. This is 3. This thing is matches exactly. Now calculate a2 using the solution. So if this is a solution, so a2 should match with 5. Let's calculate a2 using this equation. So a2 is 2 square plus 1, which is 4 plus 1 is 5. So see, this one and this one is matches. Now prove it for m term. So we use mathematical induction to prove this. Okay, this is true for n is equals to m. So what we have? We have am is 2 to the power m plus 1 is a solution of this equation of am is 2m minus 1 minus 1. Okay. Okay, now calculate am plus 1. So this is true for m. I have assumed that this thing holds. This one is a solution of that equation for n equals to m. Now calculate am plus 1 using this equation. So this is nothing but 2 into am plus 1 minus 1 minus 1. This is nothing but 2 into am minus 1. Now we know am is a solution, so instead of am I can write down this one. So this is nothing but 2 into 2 to the power m plus 1 minus 1. So 2 into 2 to the power m plus 2 minus 1. This is 2 into 2 to the power m plus 1. 2 minus 1 is plus 1. See, and calculate am plus 1 from this equation. So am plus 1 will be 2 to the power m plus 1 plus 1. See this one and this one is exactly matching. So we'll say that 2 to the power n plus 1 is a solution of 2 to the power 2 into an minus 1 minus 1 with the initial condition a1 equals to 3. If you look this expression properly, this is our recurrence relation and this is the solution, and this solution is completely determined. You can completely determine this solution because this is a function of n only. Okay, so this is how we mean by a solution. Okay, now let's stop right now. In my next video you will find how to solve recurrence relation. Okay, thank you.